What's next?
Almost had 30% of the students are not coming without you.
I forgot. I looked at the clock.
What do you do?
Algorithm.
How's your guys' poster?
Getting reprinted.
No, where's my
Big deal.
Stressful. That was stressful. Yeah. Right. Nice. I crashed from over. Wasn't gas. No, I didn't break it, but it dumped the whole tank of gas on me.
One of those rides in the rain.
I was drag racing. I mean, you guys go that way.
How was the lab, you guys?
Good.
It's good?
Pretty sure.
Perfect. Let's get into some of the examples. You'll see these in homework assignments. Remember the NOL resistor, and because the N-type is the P-type, in between you are expecting a what layer? Yeah, depletion region. And
that's cool.
yeah, and then the depletion region is going to form all these parasitic caps, remember?
Yep.
Right? Caps. And we split the entire N-well into all these little R squares. So if you model this into a RC circuit, it looks like this. Here's VL, here's V, and this is R square, and this is C square. And so VO, as we derived last time, definitely we're not going to do that again this time. So VO equals, no, the T, sorry, not VO. So TD overall from V in to VO equals 0.7. So whenever the length is a lot larger than the width, right? This equals 0.75 times R square times C square times L square. So what is L? The length, which is what? The number of squares. Okay, let's look at one example here. It's going to be very similar to the example you're going to see in the homework assignment. Example. So to calculate for time delay, right? So what is time delay? So given that this is 250 kilo ohms resistor, N-well resistor, and width equals 10. We ignore the unit right now, it's just 10. And length is 500. And the capacitance of a 10 by 10 square of the N-well to substrate, right? Just in between the N-well and substrate, whenever you have a 10 by 10 footprint there. And the capacitance is 5 femtofarads, right? So what is the time delay? A quick question here. For these two squares, do they have the same resistance?
Yes.
And this, if this is the minimum, doesn't have, since they have the same resistance, this is called what? Shear resistance, right? And
You happen to see like a black AirPod case?
no. So what about these two for in terms of the capacitance? This one, do they have the same capacitance or not? C equals what? What is A? What is D? Yeah, so the two plates, they got two metal plates, right? Here's distance, or sometimes you put T here, which is the thickness of the dielectric material in the middle. And what is this called? Yep, that's right. So that's a constant for the material, right? Silicon dioxide. So what is A? Area. Okay, so for these two, do they have the same, for this one, do they have the same D?
No. Wait, D?
Yeah, for the same process, there won't be any differences in terms of the thickness of the unwell. So it's going to be the same unwell depths for the unwells, right? So they have the same concentration and same strength, not strength, but concentration of the N-type material. It's going to form this very similar or the same depletion region, the thickness of the depletion regions. Same concentration. But area is different, so that's why they have different area, different what? Capacitance, right? If this is L, this is 2L, right? And they are both squares. If this is C1, this is C2. So C2 equals how much C1? Square? Why square?
There'd be 4 C1s.
Yeah, 4 C1. So you have 4 C1s right here, right? Yeah, just look at the area. That's the only variable, right? So that's why I have to specify that here. It's 10 by 10 square. Because it's 20 by 20 is going to be different, right? It's going to be 4 times of that amount of capacitance over here. So it's 10 by 10 square is 5 femtofarads, right? And what about this N1 resistor? It's a 10, width is 10, and length is 500. 10 and 500, okay? How many squares do I have in terms of resistor? How many square, how many sheet resistance, or how many squares do you have in here in this N1? 50, right? You have 50 squares. So what's the resistance per square? Oh, wait. That's something you need to calculate, right?
Yeah.
Yeah. Why do I need to calculate the R square? So I use this equation, right? To calculate time delay. So now let's see what are the parameters we have right now. So we have this, okay, that's the overall resistance. And you want to divide this one into how many squares? 50. So you can calculate the sheet resistance, right, or R square equals what? 250 K ohms over 50. So each one is 5? Yeah, 5 kilo ohm. That's R square, right? Each square. The sheet resistance. So how? What's the value of L here? L. 50. It's not the length. So L here is the number of squares. See, the number of squares. So L equals 50. So you have this, you have L. What is C square? The problem makes it super easy because 10 by 10, right? Since the width is 10, so 10 by 10 is the same footprint as a sheet resistance square over here. So how many? So one quick question: Are these caps in parallel in series? Since you know every single one is 5 femtofarads, right? And looks like they are in series. Are they? Why? they're in parallel. If you look at the caps in the cross-sectional view, right, they are like that, like this. So they're in parallel, like that. And they're connected in that way. Okay, if you connect them together, it's just it's multiples of the same play area, right? So if you have 50 squares in there, what's the capacitance for the overall unwell to substrate parasitic capacitor? Is that how I calculate the capacitance? So if you have C1, C2 here, right?
1 over.
Wait, no. To be confident about ourselves. So you have C1, C2, what's the overall capacitance? You got 1, you got 2, like C1, C2, right? You put them together, what's the overall capacitance? Yeah. Right? They're in parallel, so you just add them together. Parallel capacitance, right?
Because you're just adding the. Oh, you're not adding the.
You're adding areas. Yeah. You got a one cup, you got a one bigger cup, one smaller cup. You put them together here to hold. It's gonna hold like this much. Add this much more coffee, right?
Yeah.
So anyway,
That's good. I get it now.
what's overall capacitance? Let's just add them together.
Yeah.
So for each one, it's 5 femtofarads, right? You have 50 over there. Wait.
Wait.
Yeah, 250 at that.
Yeah, what's the 50 squares, each one has
5. Each one has 5. And then you add them all up. So 5 plus 5 plus 5. You can reduce that to 5 times 50. 5 times 50. So what's 25 times? Or what's 5 times 5? 25. And then you add a 0 at the end. 250.
slow.
We're all on the same page now.
Makes sense right now, right?
It's a small
So do you have everything for the to calculate the TD here? You do, right?
Yeah.
All given. Okay, so that's how I calculate the TD.
What's the
Femtol, which is 10 to the negative 15th power. What about pico?
First time I'm using 12. 12. No.
What about what's the next? Nano, right? Yeah. Anything else? All the other ones are easier, right?
Yeah.
Just micro, milli, and nothing. Bad English. The C5 layers, you guys need to know.
Do we calculate the time delay, or you just multiply it all together?
Yeah, just multiplying them all together and do the calculation.
It's always 0.35.
Mm-hmm.
That's
That's how you derive it. Just look at the notes last time. You'll know where we got that 0.35. Is that clear on this problem?
Yeah.
Okay. C5 layers. Not all the CMOS are the same number of metal layers over here, but C5, which is a 500 nanometer technology, has been very popular 40 years ago and has 3 metal layers. So 3 metal layers, metal 1, metal 2, metal 3, right? And if you look at the cross-sectional view, here's a P sub, and the first layer is called FOX, Fueled Oxide. So this is still silicon dioxide layer directly on the top of the P sub. Sometimes if you do not have any N plus or P plus being doped into the P sub, you don't need to open it up. But whenever you need to dope it, you just open it up and then dope the material to the sub. So if there's only a like metal line, nothing underneath it, right? Just a metal one. So these are all silicon dioxide layers, right? Same. So metal 1 is over here. And here's called polysilicon. It's for the gates or capacitors. And then move up, that's metal 2. That's metal 3. And then there is another very thin layer here. It's called passivation layer. But if you have so these are silicon dioxide, which is a layer on the top of that metal layer. It's not meaning, I'm not saying like this is the whole layer here is for metal 2. No, that's not right. So the metal 3 is only shorter than the thickness of that one. So this is metal 3. If you draw a wire on metal 3 layer, it's going to show something like that from the cross-section wheel, right? If you open it up, there's another layer called over glass. Over glass. And because we are drawing masks in the layout, right? So if you put an over glass layer on the top of this metal 3 pad, it's going to open it up. It won't deposit the whole silicon dioxide on the top. It's going to open it up like that, so there won't be any oxide material here. And then you can wire bond it. So metal 1, metal 2, right? And the way to connect them is through the vias. These are all the layers.
Where does the C and C5 come from?
C5, the C?
Yeah.
CMOS? I don't know. Can Google that later. So if
Are all the top layers of silicon dioxide?
Yeah.
So they're all exposed to air.
But these are not, right? They have a layer of silicon dioxide on the top.
So I'm confused here. So between M1 and M2, there's a silicon oxide between that, right?
So yeah, these are all silicon dioxide. These are all silicon dioxide.
Oh.
Yeah, and then the metal.
That's right. Okay.
Yeah, they put a shorter metal layer or thinner metal layer there first, right, for the traces, for the wires, and then they deposit the whole silicon dioxide layer, which is a little bit thicker than the metal layer, to isolate it from other metal layers. Okay, and so there might be some examples asking you to draw the cross-sectional view of the chip. So for example, if there's a layout, so this is a layout view, right? This is metal 1. And then there's another layer here. Okay, are they shorted together?
What part?
Yeah, that's a via.
Oh, yes.
Yeah, if you don't have the via, then they're not. They're just like this. 2 different layers. They're not shorted together. You need a via to connect them together. You know what I mean? Even though you have them crossed in the layout view, they are not shorted. Okay, and then draw the cross-sectional view of this layout. Here's a substrate, right? Do we have anything else below it? Yeah. Do we have a device like a transistor here or not? No. So the Fox is still there, right? It was not opened up for N plus or P plus. Then you got another layer of silicon dioxide. What is that layer for? Polysilicon. The gates. Right? The gates. and then metal 1. All right, now let's see. I'm drawing the line here. So I'm asking you to draw the just cut from here and look from the side how that looks like. Yeah, so this is metal 2, right? And metal 1 is pretty long. It cuts through metal 1, so I'm going to see metal 1 here, right? You have to do this. That's a width, that's the length of the metal 1. And metal 1 is shorter than the silicon dioxide layer. That's how it looks from the side, right? You cut from here. Think about a pie. You got an apple pie or something, just cut in the middle. If you cut from here, it's going to look different.
Yeah. So,
right? You won't be able to see metal 1.
So are we still looking at it from the side? That's metal 1, metal 2 on top of it. That's the V.
Yeah.
Okay, that's not.
This is metal 1, right? So I cut from here, from the cross-sectional view, you are going to see metal 1 because I cut through metal 1. No, they won't do it. The process is going to. Oh, did I? Sorry. Sorry. Now it makes sense, right?
yeah.
And then metal 2. Or metal 2 has to be that wide, right?
Yeah.
Then what? The via has to be that wide, something like that. All right, so that's a cross-sectional view of this layout from the top. Okay. Now let's see more examples about this.
So those are all the layers you get. So if it gets too complicated, you just have to make it bigger.
Yeah, that's right.
It's not like the PCB where you can keep just adding layers to it.
Yeah, like 40 layers or something.
Yeah, okay.
Yeah. You have to change to a different process, which is more expensive. We couldn't disclose that information, but 180 has a lot more layers than this one.
Okay.
And that's just 180, right? If you use like 20,
Right.
I guess there will be, I don't know, 20 layers or something, I don't know. Right. Look at this, one of the layout, probably not going to see if this is a piece of metal 2, and this is the metal 1. Here's a via. And in between the two connections, even though this is the metal, but there will be a little bit of resistance over there. So if you model it, sorry, it looks like this, right? M1, M2, there will be a little bit of resistance. So if you have a lot of times, you do not just use one via. Instead of using one big via, you use multiple smaller ones. It looks like this. I'll just draw it line to this edge. Optimize. I want to do it because you are going to see that in the future during the layout. So instead of making one big via, there are a couple of different smaller vias. All right.
Why are we shortening it to metal layers?
In order to make a connection.
Oh,
For some purposes, right? In the layout, in the circuit. And then it becomes, if you still model it, trying to model it, there becomes 4 resistors or 4 connections in between M1 and M2. So whenever you see a via and M1 and M2, so the purpose is to make the connection between these two metal layers, right? But instead of using 1, the software is going to directly draw 4 here. You don't have to do it yourself. If you make the connection, if you have a pretty wide metal trace, and you make the connection, it's going to generate multiple vias. You'll see that. You probably have a question, why they do that? So there are several benefits of it, right? So the first, what can I think of before I move forward? What are the benefits of using multiple ones instead of one? If if you have the same size, so we are not saying that making it bigger, okay? For example, we use the same size, just one. It also connects to metal 1, right? Just a via. Yeah, reduce the resistance. What's the benefit of it? You want to reduce the resistance because they are supposed to be the same voltage node, right? If you have multiple ones, it's like a parallel resistance. So lower the resistance. That's the first benefit. Lower the resistance.
Not wire straight. This one you have wire.
Oh, increase resistance.
Yeah, these are not resistors. These are just the vias.
Okay.
Because they are super tiny. You can imagine in the 20 nanometer technology, the vias are probably in the nanometer level. So the resistance can be pretty high, right? And what's the second one? So lower the resistance. So to keep them at the same potential, right? Or lower the current or increase the current. Is it going to reduce the amount of current, or it's going to split the current for each via? Okay, lower current for each via. Then what? Yeah. Will protect the vias. If you only have one via, then sometimes it got broken. Then what? You lose the whole connection. So here comes a third benefit. Yeah, redundancy. Right? You got some backup vias. That's the benefit of the layout. And now let's look at the layers of the transistors. Yeah, it's great to understand what are they. So if I draw, so let's look at the active layer first. So these names can be seen on electric VI side. Whenever you right-click it, you'll see these layers, the name of the layers. Before this lecture, you probably don't know what are they. The active layer does what? Opens the FOX. So if you have a substrate, right, and the FOX, and if you got an active layer here, it opens up the FOX. Like I said, when you are doing the layout, you are laying out what? Not the circuit. What? The mask. Okay. So the mask, like what I said for the photolithography, what we have been doing in the labs, I know that how these layers are being etched out from the wafer, right? But for the active layers, there must be a way that you can etch this part by using the mask here. So if you draw an active layer, which is part of the transistors layer, it's going to open up the FOX, and then it's going to deposit these N plus or P plus material into it to make a transistor, right? Or N-well, whatever. You have to open it up first, otherwise it's being blocked. Whatever the P sub is being blocked by the FOX. You have to open it up first. But for your transistor, it's not just the active layer, it has a bigger square around it. So next week, if you look at the lab, look at all the different layers from the, I think from the left-hand side, right, for the libraries, you can look at it. It has a dashed area and it has a bigger area around it for N plus or P plus material. So that one is called, if it's N plus, then it's called N select. If it's a P plus, it's called P select. So these layers deposit the materials into that window, right? After you opens up the FOX from the substrate, and then you got a little bit slightly bigger area or window to throw the materials in it. Why is this slightly bigger than the opening? So these dopes N plus or P plus materials. So why is the windows that you want to deposit these materials are slightly bigger than this opening layer? Why not just directly have the same area? You open it up and the same area to throw those materials in the same window here. Because this is a very smooth technology, right? A lot of times this can be misaligned a little bit, right? And just make it bigger, it's okay. It's okay because the whole window here is gonna, you know, accept or receive all these materials. It's fine if the material drops onto the FOX. It's not doing anything. In the future, it probably will be etched away as well. But I can guarantee that all these areas covered. If you exactly have the same area, what about this is misaligned a little bit whenever you are depositing that material in it? Then this little area won't be doped. You know what I mean? So have a bigger window so you can guarantee that the whole area here is being doped. So I have two different layers for making a N plus or P plus diffuse. It's called diffusion. All right. So unselect area is smaller or bigger than the inactive area. Unselect, bigger or smaller than active? Yeah, the active layer opens the FOX, right? But the select layer dopes, so you need a larger area to dope. And you need exactly the desired area to open up that FOX. Okay. And what about gate? So remember a transistor. If this is N plus material, right? N plus. And here's a gate. Here's a gate, polysilicon. So the question here is how these N plus materials are being doped in here. Which one should you make first? Should you N plus first and then put a gate in the middle? Do you think you can do it? I mean, whenever the channel length is down to like 20 nanometer, you have N plus, it's only 20 nanometer. And I think you can align it precise enough to have the gate directly on the top of the channel without any misalignment here.
Well, I mean, make it big enough. you won't need to worry about this one, right?
But if you make
The
it,
point is to make it small.
Good point.
so the way they do that in the C5 process is they put a gate there first. So they do the polysilicon layer first, right? And then they deposit that N plus. So this will block N plus being doped into the channel. And so it's going to directly make N plus here, right? And you don't have to align it anymore. Does it matter if you have an N plus material on the top of the polysilicon? It doesn't matter. And sometimes you use the poly layer as a resistor. Like I said, we use the N-well as a resistor, but that's not the only material you can use for the resistor for the chip. Sometimes you use the gate material, the polysilicon as a resistor. So you want to know the resistivity of it, right? Still use the sheet resistance for the two materials. They are thinking like metal also has resistance. Yeah. So what's the sheet resistance from the metal layer? The metal layer is in C5. It's usually 0.1 ohms per square. For poly, it's 200 square, which is lower than the N-well. 800.
Oh, yeah.
So do you want to use poly or N-well? Which one is better choice? So which one is the better choice? N-well, right? It's more efficient. You lay out the same footprint, you get more resistance. Usually resistors are, but sometimes you need a lower resistance. You couldn't make it through N-well, something lower than 800. How to make it through N-well? It's impossible all the times. Wait, could you? One thing here you need to know, right? Whenever you are doing layout, after a few weeks you will understand that. But right now it's difficult. But whenever the layout scales up, you want to make the connections. Let's take an example here. Okay. All right, let's look at this example. So the pink one is the gate, the poly, right? And this is a Pmos transistor, is the Pmos transistor. And you can see that sometimes you have a gate shorted to each other because that's an inverter, I guess. And I need a connection, for example, from, let's look at this one. Okay, let's look at this one. So here's a gate, right? Here's a gate. And the blue one here is metal 1. It's metal 1. And they crosses each other. So is there a short circuit? No, because there's no via. Okay, so it's okay. But based on the design of the circuit, I need to make the connection from the gate here to here. Two gates. Why I didn't directly just use polysilicon to make the connection in between them two? First, it's going to short to this gate, right? If I directly make a polysilicon the pink from here, just draw one wire, it's going to short to this gate, this polysilicon, to connect to this one. It's going to short to this gate. But if, in case that there isn't a gate here, why I didn't just directly make one polysilicon from here to here, just make the connection? Yeah. So you want to avoid long polysilicon wires, because I just said the resistivity, the sheet resistance for poly is how much? 200. What about metal? 0.1 ohms, right? So it's a lot less, a lot smaller. So that's why you, where?
Like you have that long one on the left.
This one?
Yeah, like why wouldn't you just go straight up to metal?
Yeah, because I got a metal one here, so it's difficult to draw, to put a via here. It's gonna violate the rules, so the layout rules, right? So you must keep a specific distance between two metal one layers, otherwise they are too close to each other. So that's why I couldn't drill a via here. It's gonna report errors. I have to do this and make a right turn to make it, you know, a little bit away from this metal one, and then drill via, go up to metal one, right? And then via up to metal two, which is the purple, because I got a metal one here. So I have to go up one more layer in order to cross that metal one. Two vias. Yeah, it gotta be two vias. And I believe sometimes you can directly just use the same area, the same spot for two vias. It's directly going up via one, via two. It might be fine, but I don't want to do that. Sometimes you couldn't see it really well for debugging purposes when you're looking at layouts. They're all on the top of each other with the different colors. What is that? But if you're looking at these vias, you clearly know that something like that is a metal one to metal two via, and something like this is a poly to metal one via. Right? As a metal two, then you still have to come down to poly. Right? So whenever you have a long distance in between the gates, you want to use metal layers instead of poly, right? So I think we have covered most of the C5 layers. Should be good for the home experiment. Let's look at some of the calculations for homework 4.
No one.
No, but it's poly.
Okay.
The blue is metal.
What's metal three? Do you have metal three?
I don't have metal right here. Metal is the yellow one.
Oh.
But I do have it for the ALU. Use it. You need more layers.
Oh.
These ones, right? So the yellow ones are metal three. So they're
Is that also 1 week lab or is that
it's just a 3-day lab. I'm kidding. No. I think that's a 2-day, no, 2-week. It's a 2-week lab.
Okay, good.
I probably will add a little bit more here because I want you guys to practice with making a path frame. Let me see if I have an example for you guys.
You think someone's gonna build Minecraft?
Oh my gosh, Minecraft perception.
Yesterday, some inception rules.
Which Minecraft in my
They
internet
all
class?
died at the same time that we can log out.
Logic class based on
That could be like a first year launch class.
There you go.
Yeah, so see this one. This is not within the scope of this class, right? This was an analog, but
That's analog?
not for you guys. I was trying to make a chip for my analog class. That's why I changed a lot of things in my analog class to let students design the op-amp. So here's the op-amp.
Are you going to be teaching analog 1 again?
No, I mean the correct way to teach it is whatever Dr. Jessin teaches it. It's wherever you go in the country or in the world. It's the first microelectronics class. Covers pin junctions, op-amps, and all these amplifiers with the BJTs. It's really too much. It takes the whole semester to cover all the materials. It's considered as a pretty difficult class as entry-level microelectronics class. And the second level can be the senior undergraduate, and graduate. If you get into graduate school, can be the first year graduate school. If you are taking a microelectronics major, it's called analog IC design. It covers a lot of details about CMOS amplifiers, how to calculate the gains, the outputs, and making something like that. So this is whatever I learned in that class, which is a graduate school level. You do op-amp design over there and make layouts. But it shouldn't be in undergraduate level microelectronics. And there's another one called advanced analog IC design, which is usually, if you are in a PhD program, it's the second or third year. Sometimes you take that class. All right, I forgot what I learned in there. It was a good one, I think. It's from the same book. Actually, it's just op-amp design. A lot of op-amp design, ADCs, DACs, from Dr. Baker. And there's another one called mixed signal IC design. It's a sigma delta or delta sigma. What was the name of it? ADC instead of just a SAR ADC, a different ADC. With the op-amp you design in advanced analog and use the op-amp to make ADCs. So that's what you expect if you go to graduate school for microelectronics. But anyways, this is op-amp. You can see there are not too many transistors, but if you look at schematic, this is a very simple one, not a really high performance op-amp, but just a very small one. So you see the whole schematic, right? Here's the compensation.
There's the one cap.
That's a compensation cap, right? It's a compensation cap. But if you look at the layout,
where is that?
what you'll think? Here's the layout of that schematic, right? And here's a cap. So how to make a cap in C5? What is a cap? Just two metal plates, right?
Yeah.
So how to make a cap? Yeah, but we usually don't use these metal layers for caps. Use poly. So the C5 technology has two poly layers actually. Poly 2 is not usually being used. If you are just drawing CMOS transistor, you can see all the pink traces are poly 1. But there's a poly 2. There are two poly layers. But you don't have to draw that. Keep in mind, you don't have to draw that. Unless you are making a capacitor. Here's Fox, right? And here's the poly layer. Here's poly 1. As there's no connection, it's actually not at the very bottom. Interesting. But you can draw it to the bottom, which is fine. It's just showing you you don't have to, right? So there are two poly layers you can make. Right? Wait, is that the right way to do it? All right, you don't have to. So are you actually using this part of the poly? No, you're only in the overlap area, right? So just stop at here. Then what? Via the poly 1 to what? To metal 1, right? This is metal 1, right? You got a metal 1. What about this one? So this is poly 1, P1. This is poly 2. I'm trying to make a cap. So here's how I make a cap. Here's the overlap area to hold the charges, right? And that's the via and the wire, right? And the via and the wire. So there will be a via here and connect to metal 1. So that's a cap. It's not like this, not like that. It looks like this. This is still a cap. So if we come back here, see this yellow one is a I think that's a poly 2. See the pink? Remember the pink color? The pink color here is poly 1. So poly 1 is this area here, right? Since they're overlaps, that's why they change the color to orange. So actually, this here is a yellow. Here's a yellow poly with poly 2, right? And then what? You need a vias, right? So here's a via, like a line of vias, and here's a line of the vias for poly 2 to metal 1. All right. Do I have connections to metal 1? Yeah, see? Here's a little wire, metal 1. That's poly 1. The whole line here is a metal 1, poly 1 to metal 1 via, right? So in that, because of that, I can directly connect that via to metal 1. So here's a metal 1 trace. This is one terminal of the cap. What about this one? That's a poly 2 to what? Metal 1. Do I have a metal 1 wire? Yeah, here, right? That's how I make the connections. So that's the 2 terminals of the cap. So when we calculate the capacitance of this cap, could you change D? No. Depends on the process, right? They make a poly 1 and a poly 2. They couldn't change it. It's a standard process. You couldn't change this. So the only thing you can change is what? Area, right? So when you calculate the capacitance, so first you need to know what is the unit area capacitance of the poly 1 to poly 2 cap. Then you design what? Design the area, find out the area of it, which is overlapped. It's overlapping area here, right? But not the whole thing here. Keep in mind, it's just the overlapped area. So that's the top rail, which is VDD. And here's the bottom rail, which is the ground. And you keep all your transistors, the Pmos on the top usually, Pmos on the top, NMOS at the bottom. Pmos, NMOS, Pmos, NMOS, right? So when you do the layout, you need to make sure that they have the same height. So you can keep them in the same 2 rails, top rail and bottom rail, just keep them inside. And then, you know the height here, depends on the height. You find out the height here and then calculate the length. You know what I mean? You don't want to make the cap too big. It has to be within the 2 rails. Why? Yeah, that's one part of it, important. So usually you want to make the connection pretty long to cover all the cap, the poly material, and that's metal 1 to poly 2 to metal 1. And if you make it longer, then it's going to short to the rail. That's a metal 1, right? That's a via to metal 1. If you make it over here, then it's going to short to the rail. Just keep in mind. All right, got something else, but don't have time to cover it. All right, so here is the pad frame. So for the C5, the pad, no, not that one. Okay, this one. All right, I couldn't show you because the resolution is low, but anyway, so these are the pads, metal strip pads, and I think that's 75 micron, and the whole chip is 1.5 milli by 1.5 milli. So you can see the op-amp is pretty big. Right. And then what? Where is, if you look at the, I don't have a gate. I think this little guy is probably a ring oscillator or the inverter. And these ones are the ESC diodes. ESC diodes. What's the name of ESC? Electrostatic. Electrostatic protection diodes, right? So when you touch it, it's going to discharge it to clamp it at VDD or 0, right? Or minus 0.7 volts. So I hope you guys can put the ALU in the die frame, or pad, it's called pad frame. So these are the pads, and that's the pad frame. Just put the ALU here and make the connections instead of just stop at the ALU. So you can understand how to put it into the pad frame. And after that, it's very simple. Just go to the toolbar and export that whole design into GDS2 file. I got a GDS2 file from the whole layout and send it to the foundry and pay it. They'll make a chip for you. That's it. Okay. See you on Friday.
Yeah.